Hello. Good morning. Am I audible?
Yes, ma'am.
Yes,
Okay, fine.
Yes, ma'am.
I'm sharing my screen. I'm making the record. Okay, so see, I have created the class and you must have got the notification. Okay, so you will find the details. Uh, this and the lectures. So you can access it. If you have any difficulty, let me know in accessing. And is my slide visible?
yes, ma'am.
Okay. So up till the last lecture, any queries? And I hope you know I didn't share the textbook, right? Uh, I'll share this also. I just forgot. This is your textbook, a soft copy. Hard copies, we have it in the library, but that will not be possible. So everything is online. So use this book to access. And I'm teaching from this book. Okay, you may refer if you are interested, but this is enough if you attend the lecture because yeah, so without lecture you will find it challenging to understand the book even. So just concentrate on the lectures and then see. So last time what did we do? Who will tell me in brief? You can unmute your microphone. And remember, if I pick up any name, because I would not like to go here and there, and so just to go and see and call from the list. And if I call and if you are not there, I'm going to note it down. Okay, so be careful. So don't remain present if you are not listening. And I don't want to listen that your microphone is not working or this and that, whatever. Also, no excuses. I'm telling you from the very beginning, if you are here and if I speak up the name, you have to reply. With that much honesty, you should have. That is first thing. So, Siddharth, tell me what did we do last time? Siddharth Amit Kumar. I'm just saying something and I'm getting the result very soon. Where is Siddharth? Where is Siddharth Amit Kumar? So I have to spend my time. Slide.
Uh,
Okay, anybody else who would like to help Priyank? Thank you, Priyank. Anybody else who will help Priyank? We did this. What is this slide here?
This is about the ideal diode in circuits.
Okay, so why do you use ideal diode? This is a
Uh,
model.
to make nonlinear diodes into simpler models.
Pardon?
We to convert nonlinear, which are generally nonlinear diodes into simpler linear models, so that it is easy
Okay.
to analyze.
Very good. Nice. What is your good name?
Kandarp.
Write down your ID, okay? And see, I'm going to make two kind of list where if you are answering correctly and you are participating, you will be rewarded, okay, at the end in your grading. And maybe you can get one grade up. And in case you don't reply like this, I can degrade your one grade, okay? And don't email me. I don't want any excuse after 2 years that your this is not working or that is not working and you are sorry and all. Okay, so that thing I'm not going to do. It's a big class. So as he said correctly, we are using different models. So see, this diode operating voltages are small, right? It is less than like 0.7 volt, when you talk of when you use the current equation, it is working or not working. And you and on, when it is on, it is zero point 0.7 volt, right, 0.8 volt, and that it is not like 3, 4, 5, 10 volt device. So when you are working with this high voltages, okay, and when this drop across diode is very small comparatively, so we use as a first step of calculation this ideal diode model, although nothing is ideal in the whole universe. Okay, so then step by step we will go and see other models also, but as a first step of analysis, right, we use this. What it says, it is nothing, it is really easy that if you apply something more than 0 volt, it is on, it is short, it is like a wire, and less than that, right, then it is open, means it is no current is flowing through that. So this is short and this is open. Or negative voltages. We had seen this example also, and I'm not going to spend more time in that. Now see, given this circuit here, it is behaving as a rectifier in the sense that it is conducting for the half of the pulses and not so this is an AC signal. As you can see, I'm just briefing what we did last time, right? And then what you do when you are given any such circuit, right, which has RL, C, whatever the component, and such a sine wave, you will divide your signal into positive and negative half. Okay, that's what you will do. So, and then you think of first positive half cycle and then negative half cycle, and that's how you go further and you analyze. This is a simple circuit, as you can see. But here, let's say that given this simple circuit in the exam, you may be asked that plot the voltage across the diode. Okay, so there is some voltage developed across the diode for a positive half cycle and similarly for the negative half cycle. Okay, so whatever the voltage, if you are asked to, it is versus time. Okay, so this is your T and this is your input voltage, this VI, this is the input voltage. You may have to plot for the output voltage, or the output voltage is across R, or you may have to plot across VD. So you are asked to plot across VD. Okay, so now this is for the output voltage, where you will see here across here what is your output when this is changing for the positive half and for the negative half, right? So as you can see that for the positive half, if you think, right, in the ideal diode model, what it is at 0 volt, it starts conducting. So once from 0 volt to any this positive volt up to this 0, this is like, so all this is positive, right? The diode is conducting. So diode is conducting means it is a short. Okay, so if it is conducting, it is a short. So then it is a short like this. It is a short circuit if it is conducting. Okay, and then the voltage across the diode when it is conducting will be 0. So if you have to calculate the voltage across the diode, then it is going to be 0 for the positive half. Okay, and what will be the output voltage when it is conducting? So current is flowing and it is flowing through this. So I is flowing. Okay, and what? So yeah. So now the V0, right? Your V0 is equal to IR, the current that is flowing. And that is also following this. So this is your peak output voltage V. This is, if it is V0, then your output, this is, because this is shorted, right? So these 2 points are same, you can say. And this voltage is same as your input voltage. And then when this is negative, this is going negative, right? There is no current flowing. So the current across this is I is equal to 0 because this is open. Now diode is open. So there is no I flowing. So I is 0. So V0 is 0. That's what you see here for V0. But what about the diode voltage? The diode voltage is equal to this voltage. Correct? There is no current flowing. So this, so if you write an equation, loop equation, your this voltage is equal to this voltage. So your diode current will be, right? So for the positive, it is going to be this, and for negative, it is going to be, this is your VD diode voltage. Okay, so this is your VD, and let's say this is negative, this is positive. Okay, so if you write down a loop equation, right? Then this. Now this is negative and here it is positive. Okay. Sorry. Yeah, this is so positive negative is a positive half cycle. So this is negative. So in the negative half cycle, this will be negative. Okay. So this is negative in the negative half cycle and this is positive. And when you write down this loop equation, okay, when you write down this loop equation, this plus this is equal to 0. So this is equal to minus this. Okay. So this whole negative voltage will be across this diode because the loop equation is 0. It will appear. So that's what you see here. Okay, so this is the voltage across the diode. So this is VD and this is VI, this is for VI and this is V0. So I hope you understand the difference. Whatever accordingly is asked, you have to understand the question. Don't randomly do it. Okay, and these are the voltages that is across the output here, and these both are different things. Okay, because this is open for negative voltages and hence I is 0, hence V0 is 0. V0 is equal to IR, I is 0, so V0 is 0. And if you write out the loop equation, then this plus this is equal to 0, but this is already 0. And whatever this negative voltage, it is reflected here. So this is VD is equal to minus of, so this whatever voltage, so that is this voltage is equal to this and this is negative. So that is your diode voltage. Okay, is that clear? And this is V0 upon this is known as transfer characteristics. Whatever is your input, how much is transferred at the output, that is your transfer characteristics. So input voltage and output voltage. Okay, so here from 0 volt it is conducting, whatever is the input will appear at the output and it is at a 45 degree. Okay, there is no this thing. So there is no drop. And let's say this is an ideal diode model. If it was 0.7 drop, if you had to consider, or 0.5 drop, then you start from here, this line will be up to 0.5 or 0.6 volt, whatever is, and then you have this line in parallel. Okay, so that is your, this is straight line. Okay, so this is straight line like this. Sorry, discard, let me. Okay, so whatever is the drop, if I say I mean if 0.7 is the drop, you will have a horizontal line up to that, and then in parallel you will have this line. Okay, so this is straight line. Yeah, so that way. If it is 0.7 volt, this is 0, so it starts conducting there. Is that much clear to you?
Yes, ma'am.
This is simple
Yes,
only. You have to understand the voltage across the diode, main thing. This is a transfer characteristics. This is a simple circuit and you may, but otherwise you are baffled. Okay, so by practice only, have a practice of pen and paper doing. And then this is V0 and then the voltages at different points at different nodes. At different nodes, there are different voltages. Now let us understand this simple circuit where you have one R and one this diode, and always there is a resistor. Okay, this prevents the diode from breakdown. Otherwise, if you directly connect, it will get destroyed. So there is always a resistor. And then this is a diode and this is the supply here. Now you can see that this is let's say voltage, okay, that is from 0 to 24 volt. Okay, so you have plus and minus AC signal, and this is here, and you have to apply ideal diode voltage. Okay, and plot the ID in the diode circuit. Now you are asked to plot the current ID, so which is passing, so same current is passing. Okay, in a loop always same current passes, so whatever ID it is all passing here. And that's what is asked. So you will again divide, this is ideal diode model, you will divide into positive half and then the negative half, right? and the diode is only conducting using ideal diode model, it is conducting for the positive half only. Okay, but how much is ID? So it is conducting for the positive half, and we have to find out ID. So, and then if you have to find out the maximum voltage, right, all those things. Now let us see that. So this ID is conducting for this positive, this half cycle only. But how much? So it is given by, you accept this, we will not go into the derivation. Okay, but this is given by, so now this is your circuit, it is the same thing here. And diode conducts when, yeah. So sorry. So this is 12 volt here. Don't forget this 12 volt. Okay, so this is not shorted. There is a supply here. And this is the negative of the diode. This is the positive of the diode. Okay, so now this voltage, when it is exceeding, when it is positive, so 0.1, 0.2, when this is more than this, then and then it will conduct. So it will only conduct for the voltages when it is exceeding 12 volt, right? So 12, from 12.1, 12.2, it is going to conduct. So I was also mistaken. This is not, this is a supply. If it is 15 volt, then it will start conducting when the voltage here goes beyond 15 volt. Okay, so 12 volt, then after this, the diode is conducting from here. Sorry. Yeah, I just started speaking for this like this. This is right. So this is not shorted. This is voltage here. Okay, potential. So it will start conducting after that, and it will only conduct for this much of the cycle. Okay, it will only conduct for this much of the cycle, and when it is conducting, only the current will flow. After that, no. So here there is no current. Sorry, here there is no current, and it will only flow for this much part. And how much it is, and that it can be calculated by the equation. That equation we will see in a future lecture. But for how much this duration is, this theta is how much of 180 degree total, how much this angle it is forming, this ID and all that we will see. So it is only conducting for this much part, and it is not conducting. A red is not conducting, and then this is, it is conducting for, so here it is here and here, so it is conducting this way. And similarly here, for this it is negative half, it is not at all conducting. And then this equation, this relation can be given by this maximum is 24. This is peak to peak is 24 volt. Okay, so 24 cos theta is equal to 12 volt. This 12 volt. Okay, where it starts conducting beyond that. So your theta will come to 60 degree, and this angle that it makes. So the conduction angle is 2 theta. Okay, so the conduction angle this it makes is 2 theta. Theta is 60 from this. Okay, this is maximum. This is this voltage at which it starts conducting, and it is given by this cos theta, this relation. So your theta is 120. So of 180 degree, this is one third of this cycle. Okay, the cycle is what? How much? This is your cycle. From here to here is your cycle. So this is your cycle. And it use, so this is 180 360 degree hole. This is 180 plus 180 360, and this is like 2 theta, so this is taking 120 degree of that. Okay, so this is just the conduction angle, that is the terminology that is used. This is for just information. And the peak value of the diode current. Now current, you all this given this value, you can find out the current maximum. Okay, so the peak current, so if this is peak is maximum is 24 here, right? It is changing from minus 24 to plus 24, so peak is 24. So 24 minus 12 divided by 100. Okay, so your peak current is this. So if this is your voltage, if you have I also, or you can have I here on the other side of your this axis, or on the same axis, right? This double axis I, then this peak current, it is how much? 0.12 ampere. And the maximum reverse voltage, how much will be the maximum reverse voltage at a diode? It occurs when Vs is, this is negative. Okay, so it is when it is negative. So now the loop, so when this is minus, so this is 24 in the negative direction. Okay, so this is minus, this is plus. Okay, so when it is negative 24, that is the maximum current that is developed is when this is negative, right? We saw here that the voltage across this diode when this is going negative. So this is the voltage across the diode, right? But this is in negative direction. So similarly, here this voltage is also there, right? So this voltage is also there. So this voltage plus this voltage plus this voltage is equal to 0. So this is your diode voltage. Okay, maximum will be this 24 plus 12, that is 36 volt. Okay, so that is the negative voltage across the diode that is developed. So this is minus plus minus plus, it gets added up. Okay, so 24 plus 12, and that is equal to this diode voltage. Okay, you all are with me? So KVL, KCL, loop equation, network theorems, Thevenin's, Norton's, all this you should know. I am telling again and again. So go back and see, and just see YouTube. It is not that you have to search for some book and open some old notebooks and all. Just go and see notebook, this YouTube, and see for KVL and KCL and Thevenin's and Norton's. Okay, all these things on YouTube is small little videos you will enjoy, and you will refresh whatever you had studied. Okay, so you all with me?
Yes, ma'am.
Okay, good. So now let us see here, and just voluntarily please participate. Even if you don't know, it's okay. But let us do this exercise together. And if you don't speak up your name, I'll have to speak up from that list. And I don't want a bad show from your class. So let's say this is given to you, and you have to, and then remember very much, you have to this in your mind with the bold and underline and all. Read your paper properly. If it is given ideal diode model and you are using even linear better model, okay, to get better precise answer, your answer will be wrong. Do as said in your question. Okay, so read properly, understand the question, that is more important. Spend your time in understanding the circuit. Pen and paper work is nothing once if you understand the question and the circuit. So now here also you are said that you are given ideal diode model and you have to find out V and I. So you see your circuit properly, you find out where is V. V is across the diode, remember, and I is the current flowing through the loop. And this, as you know, the current flowing from here to here is the same in the loop, same current flows. This is one loop from here to ground, okay, and the same current flows. There is a connection up to the ground, so there is a potential and the ground everywhere. The ground is there, and hence the current is always flowing, and it's the same current. Okay, so that is one thing, and the ideal diode you have to use. And now tell me voluntarily that what will be V and I here. Any
0
idea?
and 2 milliampere.
V would be 0 and I would be 2.5.
0 and 2 milliampere.
0 and 2 milliampere.
Okay, very good. So you are all, I'm proud of you. Okay, that's what I can say now. So see, for those who have in case not understood, first you have to understand that this line is minus, okay, that is universal, and this is minus, so this is plus potential of the diode. And this is the direction of the current flow. Don't forget that. Always current flows in this diode. It is conducting or not conducting. If it is conducting, then it will flow in this direction. If it is like this way, the current will flow in this direction. Okay. So here in reality, the current will flow. This is, if in the figure, if it is shown, then this is negative of this. Okay. So this is just to show you plus minus so that you can play with that. So now this is negative, this is positive, and as you can see that even after some drop, this will remain, this is plus 5 volts, so this will remain positive only. And since it is ideal diode model, we need not worry about any difference of the potential here. If the difference is like 0 volt, like this is 0.1 more also, then also this is on only. Okay, so the point is that this is positive already, so this is on, and on means it is short. It is like a short. Okay, so this point and this point is same. The potential difference is 0 here. Okay, and it is immediately conducting. Once it that 0 volt is the difference is 0 volt, it is immediately conducting. And now it is a wire, and you can know now that if you have to find out I, then it is 5 divided by this. And now this is 2 kilo ohm. So 2.5 in the denominator. I is 5 divided by 2.5 into 10 cube. Okay. So this will be 2. 5 divided by 2.5 is 2. And 10 cube goes up. So minus. So it is 2 milliamp. And always remember, when the diode is conducting, the current is in the range of milliamperes. Okay, and if it is in 0.3, you can see this exponential graph that we had seen right here. So see, this is your current. This is in always in milliamp, but here, if I mean when it is conducting right after 0.6, 0.7 volt. But this region, okay, this region of conduction is in somewhere in micro. Okay, and then this is in nano, although some current is always flowing nano picoampere. So it is always in milliamp. So once you get an answer, you should know that in milliamp. Just don't write. If the unit is wrong, also you will lose the mark. Again, I'm telling you. So similarly here, now you start afresh another problem. So here it is. This is negative of the diode, and this is positive. So from this you can say it is conducting or not conducting.
Non-conducting.
Not
Not conducting.
So I will put a cross here. It is open. Open. So I is what?
0
zero.
Zero ampere.
Zero cycle bar. And then what is the voltage here?
5 volt.
5 volts.
5
5
volts.
volts.
5 volt will all come here. Okay. So it is 5 volts. So 0 and 5 volt. So across diode. So see, this is 5 here. Okay. But diode ni across diode આવી રીતે છે. આ negative છે, આ positive છે. So you don't say -5. We say 5 because diode is here this way. We will not go and change the diode ને આપણે ઉલટું નહીં કરીએ. Okay. So this is this plus, this is -5. So across the loop it is 0. So this is +5, this is -5 is 0. But this is diode is connected this way. So we will say +5 volt. Okay. કારણ કે આ એનું નેગેટિવ છે. અહીંયા નેગેટિવ અહીંયા આવશે. Okay. The terminal is like this, so voltage it is that way, otherwise it is -5 as you see the terminal. But across diode we will say 5 because diode no અહીંયા arm છે ને arm છે. Okay. But if you remove the diode and if it is the terminal you keep, then it is -5. ખ્યાલ આવ્યો? Do you understand?
Yes, ma'am. Yes, ma'am.
Yes.
So you will write 5 only. Similarly here, this is minus here. And see, this may seem to be easy now, but now these fundamentals are clear. Now you know that okay, open say current I is 0, voltage. So now you know loop things are now forming in your mind, so things will be easy. Otherwise, you will be baffled here only. What the hell is going on? Now here it is ground, and here it is this. So this is plus, and this is minus. Okay, and this is now ground is 0. Okay, so this 0 and this is -5. So now is this forward bias or reverse biased?
Reverse.
Reverse bias.
Reverse
Reverse
bias. આને cross કર દો, open થઈ ગયું. આ open થઈ ગયું ને reverse bias એટલે.
Yes.
Yes.
Yes, that is you
Yes, ma'am.
just remove the diode and the current is what? 0.
0 ampere.
Yes, and all this voltage will appear here. બરાબર ને? જો
Yes.
see here minus means આ
Yes, ma'am.
minus terminal છે ને આ plus છે અહીંયા. Okay, and here it is, so all this will come here. એટલે આ અહીંયા 5 volt થશે. See, a minus છે, a plus છે, અહીંયા minus છે, a minus છે. Okay, so if you have a battery આવી રીતે છે. So this is minus here. Okay, and this is plus here, and so the potential up 5 thase. Okay, this is 5 volt here, and together it is 0. In a loop, all the voltages added is 0 because here the drop is what? 0. Our drop 0. In a loop, when you consider it is this -5 volt plus I into R, and I is 0, so plus 0. Okay, and then plus this is equal to 0. એટલે this plus this minus 5 plus 5. So but અહીંયા 5 છે અને the direction is like this way. આ minus છે ને અહીંયા plus છે. Okay, so it is 0 and 5 volt. So just you should be aware of this sign also. And then you will start like this way. This is minus, this is plus, and plus is 0, and minus is minus 5. So forward bias check. Then so the current will flow, and the voltage across the diode is 0 because it is a ideal diode model. And the current will be how much? This is so what will be the current across this voltage divided?
2 million.
2 milliampere.
Yes, and the direction is this. Okay, so very good. So now, you know, as I said, nothing is ideal in this whole universe. To simplify our analysis, we used it. Okay, and that is nothing wrong. As I said, if it is asked to use, you have to use that only. You need not be more precise. Whatever is asked, you have to follow. It's like an order, your exam paper. But now we want to make it near realistic. Okay, so it is still not the real one. As you know, the diode the curve looks like this. It is like this line. Okay, but it is nothing. So we are moving now from ideal one step ahead, and we say that this another model, the next step is constant voltage drop. Okay, as you know that this voltage drop is also like, you know, it is little varying. It is not a straight line really. Okay, a slanting sham. So, but here the next step from the ideal is we make it a straight line, and we say that at 0.7 it is conducting. Okay, it starts from 0 to milliamp current. It starts conducting. So this is a model. So now if you want to use it right in your simulation, then it will be replaced, and this is equal to, this is ideal diode, starts conducting at 0 volt. Okay, and this is the potential 0.7. So only if this potential positive is more than 0.7, it will conduct, otherwise it will not conduct. Okay, and why here we are keeping ideal diode? This is a diode model, and to show the direction of the current. Okay, it starts conducting at 0 volt, but we keep this symbol to show the polarity, the direction of the current. We just don't show this. We will show with this because it's a device which has a direction of the current. So this model is equal to ideal diode plus the supply. Okay, and when it is less than 0.7 volt, it is not conducting. You can see the current is 0. So 0.6, 0.5, although you will have 0.6, in reality, the microampere of current will be there. But here we will neglect that and we just go for this. We are not concerned with those small values. Okay, and it behaves like an open circuit. Otherwise, for greater than 0.7 volt, it is a short circuit. So it behaves like a switch with offset voltage created by the battery. And then piecewise linear. Now this is constant voltage drop, 0.7 no constant drop થાય છે, but still this is, you know, not the perfect one. And to be more little perfect, we will have little slope here. Now you can see that it conducts, okay, at 0.7 volt. But then there is a little there is a little change also. Okay, with the voltage, the current also changes. Okay, there is a change with the voltage. So if you 0.7, then 0.7.1, you will have, you know, this much current. 7.2, 7.4, you will have this much current. 7.5 volt, you will have this much current. So it is in point only, little difference. But you will have the current will change. Okay, and the ratio of this to this is R. You will see what is changing here is the change in the R. The resistance of the diode material is changing with respect to voltage, and so your current is changing. Do you understand? So this is known as dynamic R. We saw that in when you have a resistor or a capacitor, those device, the components, the value remains same. Even if you change the voltage, if you give a resistor whatever voltage, it will remain R only. But here with the change in voltage, although little change, okay, there is a change in R. And why is that happening? Anybody would like to help me? Why is that happening? Physics, if you go to the physics.
Because the depletion region is decreasing.
Very good, very good. This is what I was expecting. So, right, with the change in voltage now, you know that this width, right? This width will differ and it is decreasing further because the voltage has changed. Okay, and this is going to thinner out. Okay, it will be more thin, and hence there will be a change in the resistance. So, sorry, yeah. So everything is related by physics, okay? And you should know that if the area decreases, okay, the cross-section area, because that is in cube. If the cross-section area, where was I? Yeah. See, if a cross-section area is decreasing, let's say that this is a circle, okay, and then a bigger one. Okay, so if that is decreasing, I am a decrease. If that cross section area is decreasing, your R will increase. Sorry, the overall, एक minute. Yeah, sorry. It is this way only that here this is getting thinner. So this is getting thinner, so the resistance of this is decreasing and hence the current is increasing. Okay, the potential is decreasing, that means across this. When you have more voltage, this is getting thinner. The potential across this is decreasing and hence the potential across the energy that is required, the decrease thase એટલે આ barrier no potential decrease thase. See, this is decreasing, and that's the reason that you can say that R is decreasing and hence current is increasing. Okay, it is that way. This potential barrier potential is decreasing, hence R is decreasing, and that's how your current is increasing. So this R is changing. So this is known as dynamic R. Okay, so now in your real, we are going towards real model. This is still not yet a real model. And this slope is equal to 1 upon RD, and inverse of slope is RD. The resistance, dynamic resistance means the resistance changes with voltage, as I just showed you. Okay, at this voltage, the resistance is this much, and this is this. At this voltage, so the R is changing, and hence current is changing, and that's why it is dynamic, it is changing. And this is how the model is given. This is ideal. It shows how the diode is connected, the direction of that. This is VD0, that is when it starts conducting. So let's say 0.7 volt yet still. And then this is RD. And this is This is a function of voltage. Okay, it will change although little, but it will change. And this is your real exponential. So this is your constant piecewise. This is piecewise linear model we say, and your real model is an approximate. This is near approximation of this. Okay, so that's what is just a stepwise to get into the depth and the analysis. So whatever the model is asked in the exam, you use that. Now, nonlinear ideal diode as a rectifier converts AC into DC. Now, this is another topic you all know. What is rectification, and diode is used for rectification. It converts AC into DC, right? So, and we will see that in more detail later on, the applications of that in a rectifier. So, here, okay, later on. And you need, but this is just a brief of, right? So, what is, so now you know, rectification is AC to DC. But why do we need AC to DC? Who will tell me? That's my question.
Because the devices usually use DC current.
What uses
Appliances,
Electronic devices.
electronic devices.
Okay, so see, you are right. So all this electronics, especially this, now everything is made up of IC, integrated circuit, and your IC uses DC. Okay, and from the supply, current bane hydro, whatever, right? What is generated is AC. Okay, so that AC is generated, and we can also generate DC. So this power plant, now we in the beginning it was DC. So, but DC power plants it cannot travel large distances. Okay, so within a vicinity of a few 100 meters only, you produce and you use it, right? But AC can travel huge distance. Okay, so you have heard of Tesla and Edison?
Yes, yes,
Yeah. Edison was the man, a bulb and all, but then they were initially Tesla worked for Edison, but Tesla was more smarter. And Edison was like a businessman, an inventor, and a business. He has hundreds of patents, big name, right? That's why Tesla went and initially worked under him. But Tesla was even more intelligent, and then he left Edison, okay, and then they were like rivals and all. But Edison initially bulb and everything was invented, but initially he had set up in USA these plants, and they will make DC current or DC voltage only they will produce. But as I say, it cannot travel huge distances, and you have to have at every few 100 meters only it can go, and you can deliver this DC power. So, and then Tesla came with this AC thing, AC idea. And initially it was started there in USA, and it could travel huge distances, this AC power. And so from where it is produced, all of this hydro or coal or whatever, it is AC, and it travels huge distances, and it reaches your residence or wherever this big industries and all. And from there it is a high voltage, so initially you have to step down. So then at the same time transformer was invented. So it was able to do it when it from the place it was produced, it was really a high voltage. But your home in USA it is 110, here it is 230. So you had to step down, and then it has to be converted into DC. Okay, so and then that's where the diode comes, the use of diode comes into play. And now to do that, you have this diode. Now when we are applying, we will use the linear constant, this piecewise linear model, which is near to your real diode. Okay, and this diode is depicted by this. and this is your output voltage. And if you have to plot V, as I said, the transfer curve, this is input voltage and output, then this is VD0, right? This is VD0. This shows your RD term. Okay, so that is changing. Okay, and this is your V0, which is developed across this load R. So this V0, and it is a function of, it is, so now if you do simplify this, this just shows a direction of the current. Otherwise, there is nothing, this has no other significance here, right? So the voltage developed here, if it is a function, if you have to write down, it is this R divided by this in this loop, whatever the R's are. So it is R divided by R plus RD, right? So R upon R plus RD is the slope here. Okay, so, and then ideal diode as a rectifier now. So we know that the drop is 0.7 when it is conducting. Okay, so if you have to use it, so this is your VAS, let's say, peak to peak plus to minus, right? Then your V0, that is this inside line. Okay, so here this is your VD, this is the voltage. So this voltage minus this peak. What is this? Is V0. Okay, this is your output. This is your input. So here this is your input. Here is your output. This output. This is just a replica of the model here. So it is this drop. Okay, VD, this drop plus this drop. That is your VDD, the maximum drop. Okay, so that is this drop across the diode. This is the drop across the diode. Okay, तो एक तो वो जो कंडक्ट होगा ये तो है ही है plus this. So that is the drop across. So this is VDD. So it will follow with this much, and it will start conducting after some voltage. Okay, so let's say that. So that is what? That is VD0. Okay, so it will, so this difference always remains VD0. So after it has, this is starting from your input is 0, then VD0, then it will start conducting. So when it reaches here, it will start conducting. So after some time, it will start conducting, and that is always, that difference always remains. Okay, so this, at this voltage, it is just started conducting. At this voltage, it is here. So this is the diode. This is the voltage of the output. Okay, so and then that difference prevails for the peak also. So from here to here also, that is this VD0. This difference remains. Okay, so that's how, and then it is not conducting for the negative half. So once here also, this is VD0, it reaches VD0, right? For that, here it has reached VD0. At this point, it is 0. VD0. Yeah, straight line this. Okay, this is straight line, so this is VD0, so little up it is. So then it will be 0. After VD0, the current is 0. Let me redraw it. See, I hope you understand. Okay, here. So this is VD0. So after this, it is 0. Okay. So at VD0, it is 0, and then after all of this voltage, the current is 0, this line. So you have to be very careful. Okay. And then here also for all negative, it is still 0. Unless and until it has reached again VD0, it will start conducting. Okay, and it will start. So once it reaches at VD0, this point, it will start conducting that. Okay, I hope that is okay to you. Nothing big deal.
Hello, ma'am.
Bolo.
Madam, can you please go to previous slide? Madam, here is the after the input voltage is VD0. Is the slope constant over here? Means is the line is the straight line?
I don't get you.
Madam, my question is
line you are talking about?
yes, ma'am.
This line, bolo.
I mean, this line is ma'am, is this line a straight line? I was asking.
See, if you apply, we are using non-ideal diode. Here, non-ideal diode means piecewise linear model we are using.
Yes, ma'am.
Okay, where the slope is, we take this slope as this is non-ideal piecewise linear model, right? This piecewise linear model, this
yes,
is
yes.
the model here. In this model, this slope we take it as 1 upon RD.
Yes.
Okay, so this slope, this is RD, this 1 upon RD is the slope. In actual, this is exponential. Okay, so as a slope in actual, it is changing.
Yes, ma'am. Yes, ma'am.
See, actually, it is like this way. So, a slope change thase. અહીંયા change thase થોડો અહીંયા બધે થોડો change થશે. That's why. But here in this model, we take straight line, and then this is fixed. The slope is fixed to 1 upon RD. So, a slope એક જ છે piecewise માં. Okay, so that's why in this piecewise we are taking this one slope. In reality, it is changing, but that change is little.
Yes. Means in the piecewise in the model will take RD to be constant and not a function of these VDC.
Yeah. RD is constant in piecewise linear model. So this.
Yes, ma'am. Okay, ma'am. Understood, ma'am.
RD is constant and the current with voltage, the current is changing. With voltage, the current is changing. But the ratio is same. Okay.
Yes,
the ratio is this upon this is same. The ratio is same. It is a straight line. With change in voltage, the current will change. The ratio is same of this change. If you take ratio of this IV and ratio of this IV, it is same. It is 1 upon RD. Because it's a straight line. So the ratio is, it is same. But if it were this, then at every little point, right, you will have a different slope.
Yes, ma'am. That is, you were describing that the resistance changes that was for the real light, right, ma'am?
Yeah. That is dynamic. R is for a real exponential. In this case, it is R is same. This R is same, the ratio at every point.
Yes, ma'am. Got it, ma'am. Got it. Thank you, ma'am.
Okay, your real curve is like this. Okay, so at this point, R will differ, but here it will be then same. Okay, but let us see the more. So if this is the enlarged version, see, really it is like this. This is 0.7 volt. Diode will never operate for more around at 0.9 or 1 volt also. Okay, it is conducting. We conduct the voltage across diode when it is conducting is 0.7 volt. It cannot be 2, 3, 4 volts. Okay, so this is the real diode graph. This is the breakdown voltage 15, 20 volt or something, and this is the enlarged version of this first quadrant here. Okay, this is still 0.7 volt only. So here, see. Here so now this is the enlarged expanded of first quadrant. This is same. This is as it is. So for 0 less than VI, now VI is your input voltage, and then greater than, so in between 0 to 0.5 volt, it is negligible current. Okay, so from this 0 to this much, the current is negligible. And then from 0.5 to 0.7, it is exponentially. This is exponential, it is rising. Okay, so this is exponentially rising current, and then above 0.7, it is almost linear. Okay, do you get it now? This is almost straight line.
Yes, ma'am. I got it now.
Yes, okay. And then for now, this is Zener breakdown, knee current. So Zener knee, that is what we use here. Zener I will teach you at the end of this diode series. So this is Z is for Zener and K is for knee, like our leg knee. The shape is like, right, the knee of our leg. And then this is just to show the different regions. So this is the breakdown region, after which the current flows in the reverse bias direction. So we say this as VZK. Okay, so for in the reverse direction from 0 to this much of voltage, it is reverse biased, and there is a little current, right, that we had seen in the beginning. This is because of the minority carriers. Yeah, so that is the reverse bias current, that is also known as the leakage current. Okay, and for VZK greater than VI, the terminal voltage is constant. This is VZ, current depends upon, so that we will see all this breakdown and all. But so this is, after this it is breakdown, this is reverse, this is forward, and this is all in forward, it is conducting. Okay, so that's it. So what is this? This will, when it is conducting, this is the voltage across the diode. Okay, so diode is like a battery of 0.7 volt when it is conducting. And let's say that there is a diode, right, and when it is conducting, so now, sorry, yeah, yes, so here, if this is 1 volt and if it is conducting, this is like 0.7 volt, right? So there is a drop of that much, 0.7 volt across here if it is conducting. If it is 1 volt here, then we will see all those when we build more circuits, so things will be clear slowly. Okay, so now we come to the the correct equation, the equation of the diode, not correct is the wrong one, the equation of the diode, which will give you current, exact current at different voltages. So you give in the value of the voltage from 0 to positive or negative, and it will give you the exact current, for which you will get this graph. Okay, and you can see here that this is exponential. So there is an exponential term. Okay, this equation is derived based on the physics. We will not get into the derivation because it depends on the current, this carriers and the physics behind that. But let us accept this equation where this I that you see here, and this V. So V is changing, I is changing. So if you put down in this equation V, you will get corresponding, if you give V this much or this much or this much, you will get corresponding I. Okay, and that's what when you need it, right, for calculations, it will give you this exact value. And what it is, where I is equal to, it depends on all of this IS. Here IS is the saturation current, we say, and it is given, it is of the order of pico to nano ampere, and it is exponential, e raised to V upon n into Vt, and then -1. Okay, so this is e raised to Is. It is two terms, that is e raised to, exponential means you say e raised to V upon this and Vt, n into Vt, V upon, okay, -1. So you can understand this equation, and Is is known as the saturation current, and it is given in the data sheet of the diode, it is quantified. Okay, it will be, exact value will be given. Only the unknown will be for voltage, you will give like 0.3 volt, 0.4, 0.5, 0.7, and you have to find out this. All other things are known. Here n depends on the technology the diode is made, and that will also be given. It can be 1 or 2 depending upon how it is constructed. So this also value will be given. Is will be given. This Vt is also constant for a temperature. It is known as a thermal voltage. It is given by Kt upon Q, where K is the Boltzmann constant, T is the temperature in Kelvin, and then Q is the charge of the electron, okay? And that Vt, so Is is of the order of 10 raised to minus 15, or it is even less than pico, okay? So nano to some picoampere, it is sub picoamperes, okay? It will be given. Is, it will double every 5 degree, okay? So this is like the because of the minority carriers and all, okay? So it will double every 5 degrees, rising the temperature. So it is a function of temperature and not a voltage. Okay, that you should understand. And at room temperature at 25, this VT term, this VT, it is 25.8 millivolt. Okay, it is constant because when you put on this, K is this constant, T is constant, Q is constant, right? All these terms are constant. T is a temperature. Just 1 minute, give me. Okay, so then this is at room temperature at 25. This is constant, and you should even remember that. So have that practice. These things will be given. So now, so these are the values in this equation. What you see, this is given to you. This will be you will keep in this value to get I, right? And will be given Vt is 25.8 millivolt, and this is minus 1 is already a constant. And then, and it will double every 5 degree rise in temperature. That is a function of temperature. And for I, very, very greater than Is, because our I is in milliamp. When it is conducting, it is in milliamp. Okay. So when it is conducting and it is not in this very low voltage, when it is not, I is very, very greater than Is. And in that, we can approximate as, because this term, right, it is e raised to this term is already bigger. Okay, so this you can neglect minus 1. And I will be equal to, when it is in milliamp, when it is conducting, it is really greater than this Is figure when it is conducting at high voltage. High voltage here means 0.7 kind of voltage, 0.6, 0.7 volt. We can neglect this one. And I is equal to Is e raised to V upon N into Vt. Okay, it is V upon N into Vt. So this is in numerator. Or V is equal to N Vt natural log of I upon Is, if you take a natural log of this. So you can write it in terms of I. You can write it if I is Is it as a ratio of this I, and as a, you know, as this, as a, if you want to find out V from I. Okay. And as you can now understand that we are talking of this curve, right? And so this equation, if you use that equation for different V's, you will get different I you put in. So this is an exponential term, right? So you will get corresponding I. And we can write down that for I1, right? In terms of I, this is the equation. So if I1 is the current, so let's say this is I1, this is I1, this is I2, this is I1 current, let's say some I1, this is I2, similarly I3, I4, whatever. So for I1 and I2, if I want to write down the equation, then I1 is equal to this equation V1 upon this. Okay, so this is I1 V1, you can say. So this is V1, this current is I1, this is V2, this is I2, right? So for that, if I'm writing, then it is I1, then in this term, these two equations, you can understand it is the same thing. I'm just replacing I1 and I2 and V1 and V2. And then if you divide this by, so if I'm dividing I2 by I1 now, okay, then you will get, if you divide this two, then you end up with this, and taking log, When you take the log, you will get V2 minus V1 is equal to NVT natural log of I2 upon I1. See, here the goal is, as I said to you, that you vary voltage, you get current. Okay. And how much current now? Here is a measure that if my I2, if you take some benchmark that my I2 is 10 times of I1, 10 ઘણો current વધારે છે. So if the ratio is 10 times, decade of this, then if this is 10, I just replace this with 10, and VT we know. So natural log of this will be equal to this. So when you put 10 ratio here, okay, if you take some measure or you quantify this value 10 times, I2 is 10, I1 if you do, then what you will get, depending on N, you will get V2 minus V1 as 60 millivolt, and if N is equal to 2, you will get V2 minus V1 as 120 millivolt. What does it mean? That for a decade change in current, so let's say that in this diagram, see in this diagram, okay, here this is V1 and let's say this is I1. Okay, and here this is V2 and this is I2. Now this is some x value of I1. This is 10x, let's say. This is 10x. So then this I2 is 10 times of I1, you can say. Okay, so in that case, what will be the change in voltage? So this V2 minus V1, if N is equal to 1, it is just a change of 60 millivolt. Now 60 millivolt is a small voltage that you can see here in figure also. Okay, and if N is equal to 2, it is 120 millivolts. So by just changing little voltage, by little change in voltage, you get 10 times change in current. So for 10 times change in current, for N is equal to this, the change in voltage is 60 millivolt, and for the otherwise it is 120 millivolt. And that you can see here also that only voltage you change little, you will get a huge change in current. Do you understand?
Yes, ma'am.
Yes, ma'am.
Okay, and in the base, see this is natural log. If you make it in base 10, it is V2 minus V1. In base 10, it is 2.3, and VT log of 10. This is base 10, I2 upon I1. Okay, so these are the same equations. This is natural log when you are using your calculator. This is natural log. If it is 2.3 and VT log, this is base 10. And here what I'm showing you is V and I, and this as a I as a function of temperature. Okay, so you can see here that here this temperature T2 is greater than T1. Okay, so for the same diode with T2 greater than T1, you will get, if T2 is greater, the graph will be like this way and T1 will be here. I'm going to explain you shortly. And for a degree centigrade, okay, this is 2 millivolt. So the change is 2 millivolt for degree centigrade. So if it is 25 degree and this is 26, and then this is 20 for 26 degree, if this is the curve, for 25 degree, this will be the curve. Okay, and the difference is 2 millivolt for this degree, this thing, this voltage. Okay, so what I want to tell you is that you take one voltage. Let's say I am taking this volt. Okay, so if so, this is so T1 is, let's say this is 25, this is 26. So if it is 25, so for this voltage, for 25 degree temperature, okay, I get is this current. Okay, and for this voltage only, if it is 26 degree, I get this current. So for higher temperature, this is 26 degree, I get more current for the same voltage. And that is making logical sense. You will have more carriers, more bonds will break, and you will have more carriers and hence more current for the same voltage. Or you can say the other way also, that for the same current at 26 degree, for example, I need this much voltage. And for the same current at 25 degree, I need this much voltage. So to get X current at 25 degree, I need, let's say, V1 voltage, which is greater than V2 voltage at 26 degree. Is that making sense to you? You get carriers, you can get more current if you give more voltage and also at more temperature to get same current. Okay, so at a higher temperature, the voltage required will be less because now temperature is generating the carrier. But if the temperature is low and you want the same number of carriers, same current, then you will have to give more voltage. Okay, so at 25, at 26 voltage, let's say, a degree centigrade. Okay, so this is 25 degree. 25 degree. Okay, and this is 26. So the temperature is already generating the carrier. So to get the same, you will need lesser voltage compared to this. Are you understanding? You will get current because
Yes,
of
ma'am.
the voltage or because of the temperature. That's it. Okay.
Hello, ma'am.
So, bolo. With this, I will end the lecture. You can ask me if anything.
Yes, ma'am. And this VT, what is that Q? We have
It's
seen
a Boltzmann constant.
KT divided by Q.
Yeah, it is thermal energy or thermal temperature. Okay.
Yeah.
So 1 minute, can you 1 minute? Yes.
So, ma'am, one idea was spike in my mind that.
This is the temperature. T is in degree Kelvin. K is Boltzmann's constant. Q is
What
the
is
charge of the electron. And this is known as thermal voltage is VT. And
Yeah.
this is Boltzmann constant. It is a constant. This for a particular temperature, let's say 25 degrees centigrade, and the charge of the electron, if you keep in, when you put all these values, you will get this thermal voltage as 25.8 millivolt for 25 degrees centigrade.
Yes, ma'am. So, ma'am, one idea was spike in my mind that we can make one such device using this equation that determines temperature of any, like wherever diode is present, that can detect the
Your
temperature.
point is, what you want to say is that we can make it a temperature sensor, right?
Yes, ma'am. Because using
You
this
are right.
equation, we can have a V1, V2, and I1, I2. We have equation, so we can determine VT, and after that we have this constant, Boltzmann constant, and the Q, which
No,
is the charge.
your point is right. And you let me tell you, we are studying diode, but now you know that in this age of IoT, right, every day new sensor comes. And there are sensors that already work on this principle, as you have said, right? See, let's say you want to sense temperature or you want to sense pressure. What is changing is that there is R is changing, resistance. Okay. So there are sensors that work on this kind of principle, but here this is thermal voltage. Okay, so we have to now see what is changing is it is in the sensors. When you are sensing, sensor is to sense some environmental or biological parameter. Okay, and this electronic instrument, electronics is R, V, I or capacitor. Okay, so because of the external factor, like say pressure or temperature, R or C or something will change. And we have to measure this. It is easy to measure R instead of VT. Your point is correct. So if you get into more physics of that, you can find out VT also. But see, to R we will convert, say temperature. Okay, so to measure temperature, that sensor, temperature sensor, what it will do with the change in the outside temperature, okay, the R will change. પછી માં VT માં આપણે ના જોઈએ તો ચાલે, because R is changing, your current is changing, less or more. So that current in in your circuit, that current is quantified or calibrated as temperature. Do you understand what I mean?
Yes, ma'am. Yeah.
Huh. All these sensors are based on this thing only. Here we are learning this diode can be used as a temperature sensor, as a sensor which can measure temperature or any other parameter, and that's what we are already doing. But when you are, let's say, for example, having a temperature sensor which is also similar, but that sensor, it need not on and off like this. It is not a switch. It is a sensor which will sense a range of parameter. Okay, so if you get into the depth, this physics is there everywhere, and we are using that. But as I said, when you want to measure external quantity in terms of using this electronics, it is IVRC, and we directly measure this, right? And that is quantified as your external parameter. કારણ કે આપણને ટેમ્પરેચર ખબર નથી, આપણી સર્કિટ આપશે, તો R change થશે તો current change થશે, and that remains constant for if you put it in Sahara Desert also, or if you put it in Siberia also. એટલે it is a measure of temperature. એને કે એ નથી ખબર કે આ સાઇબીરિયા છે કે આ છે. So accordingly then we calibrate that. But we need not go there into the VT. એમાં VT માં જવાય, પણ પછી એ જરૂર નથી, કારણ કે આપણે सीधુं R માંથી C current મળે છે, and from that current you again calibrate that in terms of R. But your point is valid. This is that's how the temperature sensor works. This is a function of temperature, and from measuring different currents you can know, and that's how they already we make sensors using this only criteria. Because with the change in the temperature, for a constant voltage I is changing. If you measure I, you will get temperature, and that's your temperature sensor.
Okay, ma'am. Thank you.
Anything else? Then we'll end here.